Okay, hello again. So let's put the discussion of cubics, Galois group of cubics on hold for a few minutes, and let's look at something more general. Now, suppose you're in the following situation. L, K, F. Suppose K over F is a splitting field. It's a splitting field. So K is a splitting field of a polynomial over F. L over K, L over F, we're not going to assume that they are splitting fields. They might be just, extensions, ordinary extensions. Now, let's take an element sigma in the Galois group of L over F. So an automorphism of L which fixes F. Okay, the claim is that sigma sends K to itself. So in other words, sigma just gives an automorphism of K. Right? So sigma is acting on L. It's an automorphism of L. It's fixing F. What we're saying is that it would have to send anything in K to something in K. K is invariant under sigma. What's the reason for this? Okay, so for the proof, well, first of all, it's enough if you just check that. So enough to argue that sigma of K is contained in K. Why? Because sigma, well, it fixes F, right? So if I already know that sigma sends K into K, that means that sigma is giving me, well, a map from K to K, but the map is F, well, it fixes F, so it's F linear. So sigma, you can think of it as an F linear transformation from K to K. This is because then sigma gives an F linear transformation F linear map from K to K. Right? But, well, sigma, it's injective, well, on L it's injective, so it's injective also on K, an injective F linear transformation. Let me add the word injective here. Or, or you could just say, well, it's a ring homomorphism and K is a field. Sigma is injective, so it's an injective linear transformation from K to K. Is an injective linear transformation from a vector space to itself necessarily an isomorphism? Is it always a surjection as well? Well, not always, of course, but in the finite dimensional setting, yes. Now, K right? If I have a linear map from an n-dimensional vector space to an n-dimensional vector space, n-dimensional to n-dimensional, if it's injective, then it's also surjective, and vice versa. Now here, well, the question is K finite dimensional as an F vector space? And the answer is yes, because it's a splitting field. We already discussed this, right? Splitting fields are always finite extensions. If K is the splitting field of a polynomial of degree n, the degree of K over F is at most n factorial. So this and K is finite dimensional over Q. So over F, finite dimensional over F. That gives what we want. Sigma from K to K is surjective as well. So that implies that to show that sigma of K is equal to K, it's enough if you just argue that sigma of K is contained in K. And now for that, well, let's see. We assume that K was a splitting field. This hypothesis that K is a splitting field over F is absolutely crucial here. So let's say K is the splitting field of F. The polynomial F over the field F. Okay, now let's say alpha 1 to alpha n be alpha L be roots of our polynomial in K. Then K is F adjoint alpha 1 to alpha L, and as we observe, as I think I gave it to you as an exercise in an earlier video, because these alphas are algebraic, this field is spanned over F. This is spanned over F by elements of the form, well, monomials in these alphas, by elements of the form, by elements alpha 1 to some power R1 to alpha L to RL, where these Ri's are greater or equal to 0. So every element of this field is an F linear combination of elements like that. But now, see, what do we know? We know that sigma is an element of Galois group of L over F. Sigma fixes F. Right? It's an element of Galois. It's an automorphism of L which fixes F. Because sigma fixes the field F, it is going to permute the set of roots of F. Sigma fixes F, so it permutes the set of roots of F. Well, in L, but that's the same as the set of roots of F in L. Let me here write sigma element of the Galois group L over F to be clear. This implies that for any polynomial F, sigma is going to permute the set of roots of this polynomial in L. But well, the polynomial already splits over K. These are the roots of this. These are all its roots in L. So sigma permutes. Can you see if is it visible if I write down there? I think so, yeah. Sigma permutes alpha 1 to alpha L. And that completes the argument, right? Because sigma see, sigma permutes these guys. So sigma of any alpha I is an alpha j. So now when I apply sigma to an element like this, well, what am I going to get? I'm going to get a monomial again in alpha 1 to alpha L. Right? Sigma permutes these elements as well. And then, well, because every element of a K is an F linear combination of these guys, and sigma fixes F, it follows that sigma sends everything in K to something in K. So let me maybe back up the arguments here. Now, so if I start with some element, let's say beta in K, well, I can write beta as an F linear combination, a sum of, well, a linear combination of these things, right? So alpha 1 R1, alpha L RL, this is sum over R1 RL greater or equal to 0, and there's some coefficient here, let's call that C sub R1 RL, where these C's are in F. Okay, so now if I apply sigma to beta, well, that is now the sum, well, sum over the same thing, and then sigma applied to these C's, but the C's are in F, sigma fixes F, so sigma of the C is just that C itself, or L, and then sigma of alpha 1 to some power, so on and so forth. So sigma alpha 1 R1, sigma alpha L RL, right? Now, because sigma permutes the alphas, this thing here, again, well, it's a monomial in alpha 1 to alpha L. And now what we're looking at here is a linear combination, is an F linear combination of such monomials, and so it's in K. This is in K. Right, so in this step, we use the fact that here, right, so here, used the fact that F is identity, sorry, the fact that sigma is identity on F, and then in this step, we use the fact that sigma permutes the alphas. The alpha I. So I'm just making sure that we have the camera. Okay, very good. So what we showed here, this is a very important conclusion what we showed here, that if you have a picture like this, a tower of fields, L containing K containing F, suppose, so the key hypothesis here was that we assume that K over F was a splitting field. We assume that this guy was a splitting field over F. And what we proved was that if you take any elements of the Galois group of L over F, so any automorphism of L, which fixes F, that automorphism is forced to send K to itself. It can't send K to some other subfield. It has to send K actually to itself. So let me stop this video and come back in a second.